Hello, my dear friends. I welcome you all for this lecture. So today we'll discuss about the chapter number 6, Electromagnetic Induction. Okay. In this chapter, already we discussed in 4 videos the basic concept of electromagnetic induction, introduction part. After that, we have studied about the Faraday's experiments of electromagnetic induction, then the Faraday's law of electromagnetic induction, Lentz's law, and already we are discussing expression for induced EMF across the ends of the conducting rod that is moving perpendicular to magnetic field. So these all things were covered already in 4 videos. So today we will discuss about the expression. Okay, so the conductor moves in a magnetic field, then deduce an expression for induced current, force experienced by conductor, power required to push the conductor, and the power dissipation as Joule's laws, and hence discuss about the energy conservation. So I'll discuss these all things in this expression. So initially you should consider the constant uniform magnetic field. Okay, this surface is having this surface is a uniform magnetic field. So what is meant by uniform magnetic field? The every point of this surface is having same magnetic field. That is a uniform magnetic field. Then consider a rectangular conducting loop. Okay, this is a rectangular conducting loop PQRS. PQRS is the rectangular conducting loop in which the conductor PQ is free to move. The conductor PQ is free to move. Let B be the uniform magnetic field strength. Okay, so B is a uniform magnetic field. Okay, every point of this surface is having uniform magnetic field, and the strength applied, that is perpendicular to the plane of the paper and directed inwards. Okay, and it is the direction of this will be inward, and let the PQ be the moves with the constant velocity v towards the left side. Okay, with velocity v it is moving left side in this direction. Okay, PQ is a movable rod, okay, that moves with constant velocity v in left side in this direction, and then according to the magnitude of motional EMF induced across the conductor PQ, that is given by the equation E is equal to BLV, that is equation number 1. So in previous video where discussed about this, the EMF, induced EMF for the magnitude of motional EMF induced across the conductor will be E is equal to BLV. Okay, that is a equation number 1. After that, we'll discuss the expression for current induced. Okay, the expression for current induced, that is, if R is the resistance of closed loop, the induced current is given by I is equal to E by R. Okay, according to this equation, okay, I is what? I is the induced current. Okay, so EMF divided by resistance. Okay, I is equal to E by R. Suppose that is equation number 2. From equation 1 and 2. 1 is what? Equation 1 is E is equal to BLV, and from equation 1 into I is equal to BLV divided by R. Suppose that is equation number 3. So here, that is equation number 3 is the expression for current induced in this loop. Okay, so that current I is equal to BLV divided by R. Okay, suppose that is the equation number 3. So this is the expression for current induced. Then we will discuss about the force experienced by conductor. Okay, the force experienced by conductor. The magnitude of force experienced by the conductor PQ is given by F is equal to BLV. Okay, that is F is equal to BIL sin theta. Okay, F is equal to BIL sin theta. But whenever the theta is equal to 90 degree, the sin 90 is equal to 1. So F is equal to BIL. Okay, F is equal to, so that is magnetic force experienced by the conductor is F is equal to BIL. Suppose that is equation number 4. From equation 3 and 4, 3 in 4, okay, so F is equal to, I value is BLV by R, okay, that is B dot BLV by R into L. Okay, so that is F is equal to B square L square V by R. Suppose that is equation number 5. So F is equal to B square L square V by R. Okay, this is the force experienced by conductor, that is F is equal to B square L square V by R. Suppose that is equation number 5. This force acts in outward direction, that is opposite to the velocity of PQ in accordance with the Lenz's law. Okay, hence to move the conductor PQ, it should be pulled with a constant force F. Okay, according to the Lenz's law, okay, always the motion of the magnet is opposes the conductor, the same as here. This is a force, okay, this force of the conductor is acts as inward direction, and the magnetic field acts as a outward direction. So the both are having opposite velocities of PQ. So according to Lenz's law, it is true that hence the motion of the conductor PQ, it should be pulled with a constant force F. Okay, so that is, suppose the force experienced by conductor, so F is equal to B square L square V by R. Then after that, we'll see the power required pushing the conductor. Okay, so the power is equal to force into velocity. According to the equation, P is equal to force into velocity. Suppose that is equation number 6. From equation number 5, okay, equation number 5 is what? That is B square L square V by R. So according to the 5 and 6, 5 in 6 equation, the P is equal to B square L square V by R into V. P is a velocity. So the P is equal to B square L square V square by R. Okay, suppose that is equation number 7. So the power required pushing the conductor, the P is equal to B square L square V square by R. Suppose that is equation number 7. Then we'll see the power dissipated as the Joule heat. Okay, so this is what it is given by the PJ. P means power dissipation in Joule. Okay, Pj is equal to I square R. Suppose that is equation number 8. From equation 3 and 8. So what is the equation number 3? I is equal to BLV by R. Okay, equation number 3. And in 8, the Pj is equal to BLV by R whole square into R. Okay, so that gives the R and the denominator R square is there, one R get cancelled. So the Pj is equal to B square L square V square by R square into R. So the numerator 1R, denominator R square is there, 1R get cancelled, remains another 1R. So that is Pj is equal to P square L square V square by R. Okay, so that is the power dissipation as Joule heat. The Pj is equal to P square L square V square by R. Suppose that is equation number 9. Then on comparing the equation number 7 and 9. Okay, so we will get that equation number 7 is what? The P is equal to B square L square V square by R, and the Pj is also is equal to B square L square V square by R. Therefore, we get that P is equal to Pj. Okay, the power required to pushing the conductor, that is equal to the power dissipated as Joule heat. Thus, the mechanical energy required to move the conductor in first converted into the electrical energy. It converted as a electrical energy, and then it is a converted as a thermal energy. This is the according to the law of conservation of energy. Okay, so the mechanical energy is required to move the conductor in first converted into electrical energy. It will be converts as electrical energy, then it is convert as a thermal energy. So here it is according to the law of conservation of energy. Okay, the energy will convert one form to another form, but it neither be created nor be destroyed. So according to that, the energy conservation is there. Okay, so the law of conservation of energy is there in this situation. Okay, so this is about the all thing, that is about the expression for induced current. Okay, the expression for induced current is what? I is equal to BLV by R. The expression for the conductor, for force experienced by a conductor, F is equal to B square L square V by R. And after that, the power required to pushing the conductor, P is equal to B square L square V square by R. And the power dissipated as a Joule heat, that is Pj is equal to B square L square V square by R. Okay, so this is about the expression that we studied, and it obey the law of conservation of energy. Okay, the energy first convert as a mechanical energy, after that it will convert as electrical energy, then thermal energy. Okay, so here the whatever the mechanical energy is required to move the conductor, okay, electrical first it converts as electrical energy, then thermal energy. Okay, it is the law of conservation of energy is applied here. Then after that we'll see the relation between the induced charge and charge in magnetic flux. Okay, so we'll discuss the relation between induced charge and charge in magnetic flux. Okay, so here according to the Faraday's law of electromagnetic induction, according to the Faraday's law of electromagnetic induction, the magnitude of induced EMF is E is equal to d phi by dt. Okay, so the induced EMF is what? The rate of change of magnetic flux. Phi is what? The magnetic flux. Okay, according to the Faraday's law of electromagnetic induction. Okay, it is discussed already in previous videos. Okay, that is what the according to law of conservation of energy, and the Lentz's law is applied. Okay, and the Faraday's law is what it is the magnitude of EMF induced in the circuit is equal to the rate of change of magnetic flux linked with the circuit. Okay, the magnitude of EMF induced in the circuit is equal to the rate of change of magnetic flux linked with the circuit. So that is EMF E is equal to d phi by dt. Suppose that is equation number 1. If R is the resistance of closed loop, R is what? Resistance of the closed loop. Then the induced current is given by I is equal to E by R. Okay, I is equal to E by R. But the I is a induced current. I will write as a dq by dt. Okay, I is a dq by dt is equal to E by R. Suppose that is equation number 2. From equation 1 in 2, the dq by dt is equal to d phi by dt into 1 by R. Okay, the E value is what? D phi by dt according to equation number 1. Okay, just put the E value in equation number 2. Then we will get dq by dt is equal to d pi by dt into 1 by R, and the dq dt get cancelled. Therefore dq is equal to d pi by R. dq is what? Induced charge. Okay, the induced charge is equal to change in magnetic flux divided by resistance. Okay, so it is the main relation between the induced charge and the change in magnetic flux. Okay, the induced charge is equal to change in magnetic flux divided by resistance. Okay, this is the main relation between the induced charge and the change in magnetic flux. Then we'll see the next part of this chapter is eddy currents. Okay, so we'll discuss about the eddy currents. Okay, the eddy currents, the induced circulating or looping currents produced in a solid metal due to the change in magnetic field or magnetic flux in the metal are known as eddy currents. Okay, so these are the induced circulating loops. Okay, and that are produced due to the in solid metal due to the change in magnetic field or magnetic flux that are known as eddy currents, or it is also these are the currents induced in massive conductors when the magnetic flux linked with the conductor changes. Okay, whenever the magnetic field changes or the magnetic flux will be changes, okay, then the in metallic block, whatever the circle, okay, here the circular, the wave forms or circulating looping forms that are known as eddy currents, or that is focal currents. So see, in this eddy currents, these are the induced circulating or looping currents that produced in a solid metals due to the change in magnetic field or magnetic flux in the metal are known as eddy currents. Okay, so here the what are the applications of eddy currents? Okay, in induction furnace, okay, we'll use this eddy currents in induction furnace. The Eddy currents are used for met- melting iron ore, etc. Okay, and after that, these are used in speedometer eddy currents. Okay, in speedometer eddy currents are used to measure the instantaneous speed of the vehicles. Okay, in speedometer eddy currents will use to measure the instantaneous speed of the vehicles. So after that, in dead beat galvanometer, eddy currents are used to stop the damping of the coil in a short interval. And after that, in electric brakes of the train, eddy currents are produced to stop the rotation of the axial of the wheel. And in energy meters or wattmeter, the eddy currents are used to measure the consumption of energy, electrical energy. And in dia diathermy, eddy currents are used for locating the heating of tissues in human bodies. Like this, the eddy currents are having some applications. So eddy currents mainly used in the induction furnace, and these are used in speedometers, and they are used in dead weight galvanometer. They are used in electric breakers. They are used in energy meters or watt meters, and they are used in diathermy eddy currents. Okay, so like this, they are having some applications. Like this, the eddy currents are what? These are the currents that are inducing currents, or that are inducing circulating loops to produce in solid metal due to the change in magnetic field or magnetic flux in a metal, and that are known as what? Eddy currents. Okay, so because of the motion of the circular loops or circulating loops, induced circulating loops, whatever the waveforms, circulating waveforms, due to the change in magnetic field or magnetic flux, that are known as what? The eddy currents. And they are having some applications like this. Okay, they, they are used in the induction furnace, speedometers, deadbeat galvanometers, electric breakers, energy meters, and diathermy. Like this, they are having some applications also. Thank you.